So I do not know what the seal says. So I had an old seal that had no letters on it. And then I was told that I had to replace it. Well, someone fell on the web and said, you need to use a new seal. So this is the new seal. It's a couple years old, and I don't know what it says. But so if you want to tell me, Julia, what do you think it says? Yeah. Okay. So, well, we could figure that out later. All right. So I'm going to start at the end. So, yeah. All right. So, anyway, I do want to thank everybody for coming and listening to me. It's nice to be able to talk about this material. And happy birthday again, Rod. Eventually, you'll have your birthday, I hope. So. We're looking forward to that. All right. So I gave a similar talk in New Zealand about some of this material, and so I just want to start with a new result here. And so what I'm going to do is explain why I think this is an interesting result, and somewhat about this result here. So all right. So let's read it. So we have E, which is computably enumerable and 0 prime. So E is a possible jump of an RE set, right? So this first part says basically C jump has degree E, right? So jump inversion, right? That's the key thing about that. And the other thing is, I see. Okay, so now if A, so I've just built C, all right? So by the way, I'm not going to talk about how to build C. It's just jump inversion. You could do it out of SOAR. You could do it on a tree. For this proof, you'll need to do it on a tree. All right, we'll talk about that later. All right, and so then there's the so the Decker deficiency set of CA turns out to be its complement is semi-low 2. And so I'll explain what the deficiency set is and what it means to be semi-low 2 in a second, and why this is important. So that's kind of the goal of the talk, is to explain why that works out like that. Okay, so please, as I go forward, please ask questions as I go along. Okay? All right, so first we start with the Decker deficiency set. So if you have a computably enumerable set, there's a one-to-one, an infinite computably enumerable set. There is a one-to-one computable function whose range is that computably enumerable set. And that was what we had in the previous construction. It was given to us by this enumeration, so we could just enumerate this set. So just, just list it out. And the deficiency set, as you're listing this out, 0, 3, 12, 7. Okay, so this would be f of 0, f of 1, f of 2. So the point is that 1 is in my set because eventually something smaller than 12 is enumerated into my set. Okay? So it's the stages where where it's deficient. There's missing something below that number. Okay? So the key thing here is that A is RE. Well, it's certainly written. Why can't I see this? There it is. It's certainly sigma 1, so it's going to be RE. It's of degree C. Certainly, if I know C, right? If I know, I know C, I can compute. Oh, is there anything smaller than 12 in my set? And if the answer is no, then something's going to be in C. So it's going to be its degree C. And from A, I can compute. Okay, I can't point with this. From A, I could compute C. Because there's going to be, at some point, A is correct, right? So there's going to be infinitely many things which are not in C. So I just go to those stages, right? And basically F at the value I got for F at that point is correct. All right, so the one thing I want to talk about a little bit is hyperimmune. And so I missed some of the, so there's a talk yesterday. So what we have is we have a strong array. All right, so I'm just going to do it as boxes here. So we have some F0, F1, so on. And these are, the Fi's are finite sets, okay, and moreover, they're coded. All right, so they're coded as finite sets. So I have some coding for the set that's finite, all right? And now, so hyperimmune, so if that's a strong array, so hyperimmune is, so I'm going to draw a picture of it, I've got this here, is if I have my set A, all right, let's see if I could get this right here. There's no, there's no strong array that lives outside of A. So if this is my picture here, this is supposed to be omega here, and this is A. All right, if I take any strong array I have here, so this picture can't happen. All right, so that picture can't happen. What has to happen here is one of these blocks has to essentially drop into A. All right, and the point here about that, why is it hypersimple, or the complement is hyperimmune, is that if this whole block is outside of A, well, I know I could figure out this is where I need these are finite coded set. I could find the smallest element of that, right? They're all getting bigger and bigger, right? So once I have the smallest element of this block, that gives me some initial segment of A. Right, so I get larger and larger initial segments of A, so I get A is computable. So this is A. So the block here is a subset of A. So the elements that are in here in my finite set, so this is some Fi, and that particular Fi is in A. Okay. They can. So here, this has to happen is if I have for every strong array, I have to have at least one block that's completely inside of A. Okay. Okay. Okay, and the blocks all have to be finite elements. Okay. And the key, and that's why I'll go through why it's hypersimple. Why does it happen? If all the blocks are out of A, right? Each block has finitely many things. I can find the least element of each block, right? There's a least element. Let's assume they're increasing. The least element of each block. That means that A. So if I look at the value of F on that spot, the set C has been stable after that point. Right? And so I get longer and longer computable initial segments of C. Okay? All right. Okay, so that is the Decker deficiency set. Okay, so it tells you, right, how this enumeration is deficient. Right? I mean, by the way, right, if we were able to list out the set C in increasing order, it would be computable. Right, so it's basically how far off, right, this RE set is from being computable. Okay, so here is why I'm interested. So, so deficiency set A has a hyper simple superset H, then A is low 2. Okay, and so to be hyper simple, it's almost, so that's almost the same definition of this here. So now we don't have we have a different type of array. We have basically, we have these WIs, right, instead of the FIs. So they're all these arrays are disjoint, pairwise disjoints, things like that. And so now I no longer have, instead of having a finite set here, I have an RE set here. Okay? And so the key example of a hyper simple set, and well, actually there's two, there's multiple examples, is a set as being maximal. I'm not going to go y through y if it's maximal, it's hypersimple, but a set is maximal is if for every other RE set it's almost contained in A, or M plus this, well, union, the other RE set, is almost everything. Okay? So the picture would be that I draw, if I have a maximal set here, M, if I draw any other RE set, it either touch, well, I got a little bit finite there, or if I draw it, I'll do it red here. So I'm drawing this RE set. So otherwise, I've got almost everything between M and WE. All right, and so a corollary of the main result is there's a non-high, non-low 2, right? That's just from jump inversion, right? Because there's going to be some jump who's non-high, non-low 2, right? There's going to be something out there that does that, right? That's just jump inversion. Pick some E, right, such that E is not high over 0 prime and not low over 0 prime. And A does not have a maximal superset, and the complement of A is semi-low 2. Okay, so I've just gone through a complicated way to build a set that doesn't have a maximal superset that has some properties in terms of the jump hierarchy. Okay? All right. All right, so then, so sets with maximal supersets. So there's a lot of Lachlan that says that if I have an infinite CE set and it's low 2, then it has a maximal superset. All right, so I want to go through a little bit about why that is. So in some sense, I'm thinking of these are, so non-high, I'm thinking of as a lowness notion. High is certainly not a lowness notion, as far as I'm concerned. So non-high, it has a true stage enumeration. So what does that mean? It means that, well, you have some enumeration A sub s, right? So there is A. So this is, I'm looking at the complement of A. I've just listed out in increasing order, and I can approximate this stage-wise. And the point is, with true stage approximation, I have that there are infinitely many stages S, such that the approximation of stage S is actually going to be, there's a typo here. This should be A sub S, not A super S, is actually A at stage S. So infinitely often, right, when I look at the approximation, this approximation at stage S, it is correct. Okay? And so the key thing about that is that, so that tells me, so at those stages, when I am at a true stage, I know, right, things which are below, which are not in A. They're outside of A. So I have, what I'm going to call this is I have access to the complement of A. Okay, I have access to the complement of A. Okay, so that's, and by the way, okay, so the proof of that is that if you're high, you dominate all partial computable functions, right? So this is not high, so we could just kind of play around with the enumeration so we could dominate, well, the identity function of some sort. So this enumeration, this A sub S is computable in A, and therefore there's some function that doesn't dominate. All right. All right, so now low 2-ness, which is certainly a lowness notion in my mind. The set of E such that WE, so the set of X such that W, so the set of E such that, first of all, well, this is, I have to be careful. This says that, well, I want this set to be infinite. This is a set of X which are in WE, not in A sub S, so not in the approximation at the stage types are in WE, and S is a true stage. Right, so I'm looking for the set, so I'm looking at true stages, and I want to know, on those true stages, do I see infinitely many things which are in WE, but not in A? Okay, so these things, by the way, are certainly, because they're at true stages, these things are certainly, and I should be careful here, this should be, I should have here that really X is less than or equal to A sub S at this stage. So that's missing there. All right, so these, if I see that set, if I see that happen, then I certainly have infinitely many things that are in WE. So this implies that there exists infinitely many x, such that x is in WE minus A. All right, so there are infinitely many things which are in WE outside of A. Okay, so I consider that as informational. All right, so that's informational that I get. And so, okay. So those are the two aspects that we need for this proof here. And so, okay, what does this give us? So this is in some sense important here for this construction, which I'm not going to go through. So I could use zero double, and I ask for each, that should be SE, I'm sorry. For each W, is this set, if I give you some WE, oh, well, I'm sorry, this is for the set W. So I want to know, is W infinite outside of A? All right? And so zero double can answer that question. Okay, so I have some W which is infinite outside of A. There it is. And then I ask, okay, yes. So now what I'm doing is I'm guaranteed for all K there's going to be some stage such as at least K balls X where they're inside W, right? Not in, okay, so now not in my maximal set that I'm trying to build my superset, and A is a true stage, right? So I kind of changed the question a little bit here. So I'm trying to, M is my superset of A. I'm trying to build this, right? So I have enough, I could ask these type of questions. This is RE, ask this here is RE. And certainly is this is RE in A, because I'm asking whether it's a true stage, right? So the key thing is this is RE in A, not R, so it's RE in A, because asking whether something is a true stage I need A to figure that out. So this is RE in A. And so what happens if the answer is yes, what do? I basically get for every K there's going to be at least K balls where the things are in W outside of M and it's a true stage. All right, so the point is if it's at a true stage, these X are not in A. All right, but the problem is what I don't have is I have no way to figure out how long it takes for basically the K plus 1 ball to appear to stabilize. I just have this approximation to A sub S, and I just have no idea how long it takes for the ball to stabilize. All right, that's the key thing about this. I have no idea how long that will happen. And this is going to be a problem. Well, all right, so basically I've called this an imperfect stream of balls outside of A. I know that I have infinitely many balls behave this way outside of A, right? I could find some of them, right? But I just have no idea when I have a ball that's outside of A. Okay? Now, after the talk yesterday morning, I thought about trying to, well, it'd be nice to be able to describe this more, and we'll see how this impacts what I'm talking about. So right now I have no way to describe this. All right, so this is, okay, so that's what we get from being low 2, all right? And so now how does Lachlan use this? So basically, the way Lachlan uses this is what's called a chip construction, or what Sorel would call a trip construction. And so infinitely often we get verification that this set is infinite. And what we do is, oh, I think that, so it looks like W should look like this red set rather than the purple set I drew. Right? So I'm going to toss everything that's not in M. Right? So I got some set A living down here someplace. And I could just, so I'm building, remember I'm building M, and I have some set A that's living down here. So I say, oh, I've got a bunch of balls in WE. I could toss everything else into M, and I'll still have plenty of room to move on. Okay. So I'm not going to go through the action too much, but basically what happened is I took one action on this stream. Okay, I just took one action, right? I tossed everything that wasn't in the stream into M, and I left this. But what I couldn't do is I couldn't take this stream of elements and divide it into 2. And this will become more clear later. All right, so I'd like to take half of it and put it into some, say I didn't want to build M, but I wanted to build some other set, M1 or M2. I couldn't take half and split them one into I couldn't build them into different disjoint sets outside of A. Right, so my picture here is that Here's A, right? Now I have a bunch of set balls that are hanging out like this, and I like to say, all right, I want to capture half here and half here. I can't do that. At least I don't know how to do that yet, right? We'll see, okay? So I can't take that action. Okay. All right, so now we're going to talk about an old result of SOAR. So the outside of A, or L of A, is basically it's the collection of all RE sets, which are including A under inclusion. And so this is the lattice of RE sets, that people like to call it. Right? I just call it the RE sets. So E is the structure of all RE sets under inclusion. Right? And so basically, if A is equal to the empty set, then L of A is equal to just E. Right? So I should also have added here, if A is computable, then L of R is just also equal to, so if A is, so if R is computable, coinfinite, we also have the L of R is equal to E, just by mapping everything to the complement of R. Okay, so I'm going to view SOAR proved that if A is low, then L of A and E are isomorphic. Okay, and so the question I want to explore here are for which A is L of A and E isomorphic? Okay, and it was conjectured years ago by a number of people, at least one who's in this room, maybe they remember, maybe, that A can be any low 2 set. Okay, so I perceive this question is about lowness, right? Because basically, at least in terms of this question, if L of A is isomorphic to E, then it looks like a computable set. Okay. So, and also because of the notions we need to prove this, this also turns out to be about lowness notions. Okay, so what I'm claiming here is, what I'm saying here, if A realizes one of, or some of our lowness notions, then we want L star of A and L of E to be isomorphic. Okay? And now why did I talk about maximal sets? Maximal sets do exist. I'm not going to prove that. It's Freeberg. Right? So if L of A is isomorphic to E, then A must have a maximal superset. There has to be a maximal superset. Right? So I'm really interested in things that have maximal supersets. Okay? That's what I'm interested in. All right. And so here's what the new result is, right, in this terms here. So there's a non-high, non-low 2 C set such that L of A is not isomorphic to E, right? Because A had no maximal superset, so it can't be isomorphic to E. Right? And then the part we haven't talked about is semi-low 2-ness, right? So A complement can't be semi-low 2. Okay? So that's what I wanted to get out of the result from so far. Okay. Questions? I'm probably going too fast here. All right. Okay. All right. So what I want to do is I want to reflect a little bit on SOAR's proof and what he needed to prove this theorem. All right. And so to do this, we needed infinitely many balls outside of A. Right. So we want to be able to play with things that happen, outside of A in this region here. And so the key thing so I'm going to divide this up into information and access like I did before. So the information came because I'm using semi-low 2. So what I want to know is basically if there are infinitely many things, if WE intersect B is infinite. So this is pi 2 in B, right? This is pi 2 in B, right? And so B could be anything, but I want this to be computable and 0 double. Right? And so in particular, I'm interested, so if A is low 2, right, then this is pi 2 in A complement, so that's going to be semi-low 2. Okay, so if A is low 2, its double jump is 0 double, and I'm looking at basically something which is pi 2 in a complement of A. All right, so I should point this out here is that I'm considering this as a lowness notion, right? It's not a property of 20 degrees. It's a property about the RE set. Okay, it's not. So it's a property about the RE set that we have that's going on. And I should point also out that by a number of results, including some of Rod's, all these nodal notions are disjoint from each other. And they're kind of disjoint in outside of the low 2 degrees, they're disjoint in every degree. All right, but we're not going to talk about that much here today. Okay, so that's the informational thing. So this is really, so back here, if A bar is semi-low, that means that I could find out if there are infinitely many balls in WE such that there are infinitely many balls in WE outside of A. Right, so I have information about the outside of A. Okay. All right, so now access to A complement. So so I need another definition. So semi-low. All right, so semi-low is a slightly different question. All I want to know is if I have A bar, is WE intersect A bar non-empty? Do I get one thing in at least one thing in WE that's outside of A? Okay. So, and I want that to be computable in 0 prime. And the point is that this, again, it's a sigma 1 question in A bar. All right, so if A is low, right, this question is certainly delta 0, 2, right? But again, I'm not going to go through it. You could find semi-low sets in every RE degree. All right, so again, this is the notion of lowness. Okay, and also, by the way, outside of the low degrees, there are also sets which are not semi-low in every non-low degree. Okay, so how do we use this? So I want to go through this proof a little bit because this is what we get out of this. So so what do we have here? We have so all right. So I'm going to think of it like this. So I have my set A. Okay, and I want to split A up into some. So I have some collection of balls that are entering in here. So let's just call this W. All right. So I know that W outside of A is infinite. So So I know that there's infinitely many balls over here. Right, so I get to see how they enter, right? So what I'm going to do is I'm going to build, I'll just do it like this. I'm going to build these sets F0, F1, all right, F2, so on, right? So this is going to be a finite array that I'm building of sets, all right? So it's just like I did before to be hyper simple. What do? I want to make sure that there's some element here hanging out in each one of these things here. And every element that I put into the set W goes into one of these things here. So what's going to happen here, if I have some array that looks like this, and at this stage I'm seeing this, and also because I have the limit lemma, right, I could ask, is this really going to be empty? And if the answer says yes, at this approximation stage, what I have here, I just put the next element that shows up. So I have this list of elements that are appearing going into here. I put the next element into there. All right. So when I think that this, right, when I think that Fi is, so when I think that basically Fi is contained in A, I bet add the element to Fi. All right. So eventually, right, if it turns out to be empty, right, then 0 prime will tell me it's always empty, and I'll add everything into it, so it's going to be non-empty. Right, so eventually I'm going to add something to Fi that's going to be in there and stay in there. Okay, so each one of these, so that's the idea here. So each one of these things has, there could be finitely many elements in there, but at least for each Fi, I know it contains one element, at least one element outside of A. Okay? That's the key thing. All right? And so I went through the construction. So, all right, so what I'm saying here is each Fi provides finite access to the outside of A. Right? So in other words, if I work with this Fi as a single ball, I know I have one element that's outside of A, at least one. I might have multiple ones, but I have at least one. Okay? I have a thing to grab onto. All right. So now I want to reflect back what I had in my original ones with the true stages. So with my true stages, I don't have this finite access. Right? It doesn't stabilize like this at all. Okay? And also, I could put, because these are all disjoint, pairwise disjoint, I could put every other one of these, or whatever I want, into one set, and the other one into another set, and everything's good, right? So I could split the stream into two. Right? Once I have this finite array, I could do whatever I want. I could rearrange them, do all kinds of stuff. All right? So it's actually very powerful. Okay. So that's what SOAR proved, or that's what SOAR used. Okay. All right. So I should point out, by the way, so A being semi-low implies that A is low, semi-low too, right? So if you're semi-low, you're also semi-light too. So you have the informational thing I had in the slide before that, and you have access to A. And then SOAR showed that L of A and E are effectively isomorphic. So who cares about effective right here? Okay, so that's what SOAR showed. All right, so then Moss improved this. I know these are old results. So if you're semi-low 1.5, all right, now again I'm asking whether WE inside of B is infinite. And this just turns out to be, I want this to be basically a pi2 question. All right, to be semi-low 2, it had to be computable in 0 double, right? But here I want it to actually be a pi2 question, right? You know, so uniformly a pi2 question. Okay, so how I got the information is important. So it turns out that this is stronger than semi-low 2 and weaker than semi-low. That means the complement of A being semi-low, the complements of these things being semi-low. And so Moss improved SOAR's results, saying that basically if A bar is semi-low 1.5, then L of A, and these guys are isomorphic. Okay, so I want to reflect a little bit about why that happened. Right, so this is an improvement of SOAR as a result. And so Moss needed, again, information, we know how he gets it, but also access. Question, guys? Good? Sure? Bach? It's okay.
No, it's different. I was asking about Moss.
Oh, I don't know anything about him. Not true. I don't think he did other theorems after that. But yes. What? So okay. So yes, they are effectively isomorphic. This might be a conversation to be had later. I'm sorry.
That's why I said go ahead.
All right. So they are effectively isomorphic, but that's really, again, I'm not so interested right here. But so Moss improved this theorem, and so what I want to talk about how Moss got access. So I want to define this definition here. This maybe you've seen this, maybe you haven't. Maybe there's probably what?
What's OSP?
OSP. So OSP stands for outer splitting property, but since everybody's like, what is that? I'm just going to OSP. Okay. So OSP is this theorem here. So basically what I defined here is a sieve for W. right? What does it mean to be a sieve? I basically have a collection of pairwise disjoint RE sets. Okay, now instead of these were finite over here when I collected this for being semi-low. So now I just want these to be RE, right? The union has to be everything, and for each I, WE, well, so each FI, right? What's outside of A is finite but non-empty. So essentially this picture here, except having finite sets, I'm allowed to have RE sets. Okay? And so if you actually have a sieve, that basically witnesses that A is not hypersimple, right? Because if you had such a strong array like this, if you're hypersimple, one of these has to be completely contained inside of A. Okay? So, all right, so this is, again, so a nodaless notion. And so what happens is OSP is essentially the property that for every RE set, there's a sieve for it over A, and that could be found uniformly. So given WE, I could uniformly find this sieve. All right? That's what OSP is. All right, so that's what it's used for. And so, by the way, I should point out here, if A has OSP, it cannot be hypersimple. Okay, that's very important. Well, it's not that important. And so Moss proved, this is a beautiful result, Moss proved that if A complement is semi-low 1.5, then it has OSP. Okay, and so the key thing about that is any stream of balls outside of A can be split into two such streams uniformly when A has OSP. I could just split these things up. I have access and I have control over these two strings. Okay. All right. All right. Okay. All right. So when I put in the slide, it asks for a title. So I have a title. All right. So I wrote classic here because this is something I proved in my thesis. So if A has OSP and A complement is semi-low too, then L star of A and E are isomorphic. Okay? So, all right, so that's something I proved in my thesis. All right, so basically, I think that's the max you could do in terms of access and information that we have. All right, that's something that I'm asking about here. And so the corollary, the main result says, well, remember, well, let's go back to what we have so far. There's a corollary. All right, so remember, now we know what semi-low 2 is, right? So, and also non-high means I have a true stage enumeration. Okay, so let's go forward here. So the corollary here is there is an A with a true stage enumeration. All right, A complement is semi-low 2, and L of A is not isomorphic to E. Okay, so I needed OSP. Okay? Now, so we know that true stages cannot replace OSP. Right, that's kind of the point of this. All right, so, all right. I mean, I kind of knew this when I wrote my thesis, but I couldn't prove it. Right, so that you needed OSP. So, okay. So where does this leave us? So there are low 2 sets without OSP. So the question that I would like to address is if A is low 2, are L of A and E isomorphic to each other? Okay, so I think not, even though it's conjectured otherwise. All right, so here's some ways to maybe attack the problem. So is there some findable property P such that P, the empty set, holds, but also fails for the complement of A? Right, so I suggest something along the lines of I can't split this imperfect stream into 2. All right, so I don't know how to write that out yet. All right, I'm still doing this. And I realized after I'd written this talk and thought about this might be the answer or question here. So it could be the fact, do I have an atomless hypersimple set? So I didn't go through the details here. So if so if A is hyper simple, that's really if and only if L of A. Now I have to mod out, so I'm going to mod out by the finite, mod finite, right, is a Boolean algebra. Right, so what's that? Again, Lachlan, right? So that's what it means to be hypersimple. So being hypersimple is a definable property. So can it be atomless, right? So I actually don't know, right? So what's the key kind of thing about atomless versus maximal? Well, in a picture, so here is A. Now, if this is going to be an atomless Boolean algebra, I have to be able to split it. I have to split mega into two. I have to split everything into two, right? So, and I don't know how to split anything, right? So, I realized this just before I got on the plane, among other things. So I don't know how to solve this problem, right? I will point out that the question I did answer, I asked, and no one else answered at Rodfest in New Zealand. So, I guess in the next Rodfest, I might be able to answer this question. So, I think aren't we iterating this, right? All right, so I don't know. So I'm actually conjecturing that it's false, right? And in fact, that's why I did say the end of the line, because I think that. All right. Now, I will leave open the possibility, the likelihood that I'm incorrect. And so maybe it's true. And so, okay, so the key thing here is it's the modern isomorphism method, which I'm not going to go through this, needs the finite access. You can't get rid of it in the things. And it needs the ability to split a stream into two. All right, you can't get rid of that in the tree construction of an automorphism. Okay, so if you're going to do this, you would have to go back to Soar's old effective isomorphism method, which is hard to understand. And it's very effective. It's a beautiful method. And get that to work, and you're going to have to add in chipsets, some way to get this information from 0 double, all right? But this is the problem is these chipsets are generally pi 2, and here they're going to have to be delta 3, and it's not clear you can make that work. All right? So,
You're thinking of that on like some weird skeletons.
yeah, some weird skeleton. So the thing is that if I know you know the effective automorphism, right? You're taking action and you have like lists of things that are going on. And then you have to have, you're getting information from the chipsets. Do this with these lists, right? So, by the way, I would consider this argument a chip argument, because our approximation for 0 prime either saying it says, oh, WE is empty or non-empty at each stage, and then it changes, right? So eventually, because every WE is going to be non-empty, is always going to be, oh, it says it's non-empty, right? So each time you change, that's like getting a chip. Okay? So, but that's a chip that's computable in 0 prime, not a chip that's computable in 0 double. I don't know how to do these type of chips with delta 3 offhand. So it's got to be some kind of effective argument probably, or some skeleton going on. I don't know. I don't know how to do it. Okay? So, but that's why I'm conjecturing it's likely false. And so in the third iteration of Rod's birthday, I hope to have an answer to at least this question here. Right? I have not been able to answer this question. And I will say that it's the reason I did the old result is back a long time ago, is I could not figure out how to prove this result that was conjectured at the time. So I did prove this one instead, but I couldn't prove the other one. And so I don't know how to prove it yet, and I guess it's bothering me a little bit now, so I'm going to try to figure out the answer.
Yeah, because it was stronger than predicted, but it was announced by Saul and Harrington, so it's the gold result disproved the unemployment.
Is that right? I don't remember.
Yeah, it's in Bob's book.
Anyways, all right, so this is the end of my talk since I started with the end, so this is the beginning. Thank you very much.